Here's the thing that I'm going to call recode. I'm not sure what else to call it, but I keep describing it and I need to give it a name because it's annoying to say a bunch of words over and over again to describe it. This is how I go from not knowing how to solve a leet code or blind 75 type problem to being able to type out the answer as quickly as I can type. And the limiting factor is like how fast can I move my fingers, how fast can I type, and in my mind, I'm able to generate the solution and the individual things that I want to type as quickly as I need to. At a high level, it is a bunch of steps. Recode is a bunch of steps to clarify and solidify a solution to some problem. So, for clarifying, what I mean is get to the point where I understand concrete steps to solve the problem, and if needed to, I could even like make changes to the steps. So for example, skip vowels, um, like take the original problem and then just skip vowels if that's somehow applicable to the problem. Solidify, so I want to clarify and solidify. Solidify means able to recall very quickly and accurately what all the different steps are. And at a high level, the steps are working that you work from a low level to like really low level concrete steps to higher level description of the problem. And the reason for that is it's a lot easier to remember the high level description. There's not as much to remember, and if I can get to the point where if I remember the high level description, I can generate the individual steps, then that makes it so I don't have to remember as much. So the concrete steps of recode are: first, find a problem that I don't know the answer to. In this case, I'm going to demonstrate on a problem where I probably could have made the answer, but I want to start off with something where I don't actually need this process, this recoding, just to practice the steps of recoding and demonstrate what they are. Um, and then, so what I'll do at the very beginning is make a copy of the solution. Um, so in this example, um, I'll be using build graph. So the specific problem that I'm going to be working through is if I have a list of edges, then I want to create an adjacency list. Um, and so that looks like this. So here would be a list of edges. So this means that there's an edge between W and X. So if I'm at W, I can get to X. If I'm at X, I can get to W. That's what an edge is. So here's a list of those. And what I want to end up with is an adjacency list where I can, given any node, I get a list of all the other nodes I could get to from that node. So in this example here, if I was at W, I could get to X and V. So if we go back to the original here, we see that here's an edge from W to X, and then there must also be, here is another one from W to V. So an edge from W to X and an edge from W to V. So that's why we have, if we started at W, we would go to, or the things that we can get to, the nodes that we can get to are X and V. So that's the problem. And I already have a solution, so I'm going to save path solution.js. So I save a copy of it, and then here's the original. So I just saved the copy as shortest path solution. That's this step. Then I will go back to the code, and I always start with the innermost lines of code because those are usually really what I want is the most concrete lines of code, and then I'll comment each line, and then after commenting the line, I will delete it and recreate it. And once I comment an individual line, then I go to the next line of code and keep doing that until I've filled out a whole block of code. And then I go up a level of indentation. So for example, here, let's go look at this code. This is a really innermost line of code, and it's the only level one. There's no sibling lines of code. So after doing this line of code, if I write this comment and then am able to recreate this, then I would work my way out to this if statement. And once I do that if statement, then I would move on to this if statement. And then, so for doing that, I would start at the innermost line of code, then work my way out, then go down here, and finish off with these two. And then once I'm able to do all of that, then I would work back up one level and do this for loop. And then once I do that, I would do all the things that are at the same level of indentation as the for loop. So let's see what else there is. So there's not a whole lot at the same level as the for loop. So once I'm done with that, I'm basically able to rewrite the entire function in one go. Let's see. So work towards higher, less indentation until able to rewrite the whole solution from just the comments. And then ideally, I would be able to remember the comments, so I don't need the comments. So I could, if somebody were to ask me the initial question, so if somebody were to just pose this problem statement to me, would I be able to then go ahead and write the whole function? So let's go ahead and try that out. This code already has a bunch of comments, so I'll just delete them and then start adding commentary. The goal with the comments, it would be nice to have a comment that is more and more like a high-level description of what the line does. But if I need to, I can start off with a very concrete thing that is actually happening in this line. So here, for example, I might say, put into object graph at key B an empty list. So if I do that and then I delete this line of code, if I have this line of code, then, or this comment, then I just need to know how to program in the language. So I know that I need to make that there's an object called graph, and then I want to at the key B oh, actually, I guess I need so at the computed key B, an empty list. So then I would put something like that. But ideally, I wouldn't put something so concrete. I would work my way towards being able to say, like, what if I was describing this to another human, what would I say about this line of code? Well, what's going on here at a higher level is the graph for the key, for the node B, it starts off with an empty list. So node B should start with an empty list of neighbors. Or another way of saying that is something like node B has no neighbors to start with. So notice this last one doesn't say anything about how I would indicate that it has no neighbors. Maybe in other algorithms this would be the number 0. But in this case, we're trying to keep track of what the neighbors are, so we could keep a list. Maybe we could have a set here. That seems like a reasonable thing to do as well. Actually, now that I've said that, yeah, that's a change I could make. So going back to the steps, so I'm at the part where I made a copy of the code. I will comment the innermost line of code, And then, so I've commented the innermost line of code a few different times. Ideally, I would just do one of these and then delete the code and then rewrite it. I did that too. And then I would work my way to a higher level. So that's this. Here I want to say check if key B is in the graph already. So that's like a somewhere in between low level and high level. Maybe a little bit higher level would be if there are no neighbors tracked for B yet. That's like an English way of saying this line of code. And now I should be able to delete the lines of code and hopefully recreate them. If not B in graph, then do these two lines of code. Then B has no neighbors to start with, so we'll do that. And I could even get to the point where I mean, ideally, this is what I'm headed towards. If not B in graph, I'm headed towards being able to have no code at all and just the comments, and then even better, have no comments and still be able to recreate all of the code. So if not B in graph, then we'll do graph at B now has an empty list. Yeah, that seems good. And so now that I've done this if statement, I'll do this one. The reason that I did this one first instead of this one, I don't know. It's just the order that I saw them. So the code is nearly the same as this one, and the concept here is also nearly the same. So node A has no neighbors to start with. So I'll delete, and then I'll go here and I'll say, actually no, I won't do that yet. Graph at A has no neighbors. Okay. And then another thing that is nice about doing one line at a time rather than, so for example, another thing that you might try, another thing that I have tried is comment everything and then go, and then write all of the code. And I don't do that. And the reason is if I comment one individual line, then I can, and then I recode it, then I can go write the, I can run the tests again. Maybe I should put that in here. So comment out the solution. After commenting out, run the tests again. Yeah. Once, actually, I'll say run the tests again. Run the tests after rewriting every line of code. Ideally, there would be some sort of test runner running the tests for me, and it would just pop up something telling me that some test fails when it fails. That would be cool. Yeah. So the test here is it will print something out if the test fails. So if I go mess up the code here, let's do, I'll do an incomplete empty set, and then I'll rerun the test. So that causes an error to happen. So that's good. So that means changes that I make here are actually affecting the test in some way. I would actually like to see what it's like to do this with a set instead of a list. I think that will that'll be a good example of how recoding gets me able to do changes to existing code. And if I can do changes to existing solutions, um, that's what it means for me, or that's the thing that I want out of understanding the code. Um, okay, so let me go finish this off. Maybe I should. Okay, so here, so if there are no neighbors for A yet, so that's what this line does. Then start node A with no neighbors. Okay, let's try that out. Can I rewrite this all from scratch? I think so, especially since it's really hard not to just look at the code that I wrote below. It's also hard to type. Okay, and then we'll do graph at A equals that, and this comment goes there. Okay, cool. So now I've done all of that. Here we are grabbing out of edge. We are grabbing an individual, the two nodes from that edge. And actually, I could do this like this. A, B. That should also work. Let's go find out. Oop. There we go. Yep, that worked. Cool. So there's another slight improvement on the way the code was written. Let's try commenting this. Or no, we're not there yet. So I've done this and this. Now I want to comment these lines of code. So what's going on here? If I were to describe this, well, the individual steps here are in the graph at node at computed node A, add put node B on the list of neighbors. Okay, so that's what this line does. Graph at A dot push B. Okay, that all seems good. And then here we can do the same thing. Okay, so I'm going to try to rewrite it without the other comment right there. So let's see. Add to B, B's list of neighbors, the node add A to B's list of neighbors. How about that? Yeah. Okay, so graph at B, that gives us B's list of neighbors, and we want to push onto that node A. Okay, that seems good. Let's see if the test goes. It does. Cool. Every time I run the test, this is what success looks like. If it doesn't output anything. Okay. So I think that is everything inside of the for loop. Yep, it is. Okay. So now I'll say for every node A and B in the list of edges. That's probably why I had it split up, is it's kind of hard to comment this turning that into this code. I don't know. Seems like there's a couple steps going on here, and it could be broken into more steps to make it easier to write what each step is doing concretely. That's probably why I had it in several lines before. Okay, so can I rewrite that line of code? Let's try it out. I was hoping at some point I would come across something where I would have to reference the original const AB, const AB in the list of edges, in edges, or is it of edges? Oh man, is it in or of? In for A in B. In Python, that means for every element in a collection. For what does it mean? Oh, here. This I remember now. Okay, so in JavaScript, A in graph means A is a key in graph. Not the letter A necessarily, but whatever A represents as whatever the variable, the value associated with A, that key, that value, is that a key in graph? So in means, I think that's not what we want. We want for each element of. I think in JavaScript you want the word of. Oh, ha! This is a place where we can go look. Of. Okay, it is of. Cool. Okay. So I think that worked. Let's go try it out. So I just looked at the solution, and the solution had the word of. Solution, and it has the word of. And I looked at the solution because I was having trouble remembering whether to use of or in right here. In Python, this would be in, and in JavaScript, it's of. Let's see. Now, what do I want? Another thing that I could do is say in, and then go run the tests, and I would see that I get the wrong answer, or that it doesn't work for some reason. I don't know exactly what the problem is, but the fact that it prints out anything means that it failed somehow. So yeah, so I'll change this back to of, and then go back and run it again, and now it works. Okay. So here, create variable graph, and start it off with an empty object. That would be a very concrete description of what's happening here. And at a higher level, I might say something like, well, so first, can I recreate the code from that very concrete description? Const graph equals an empty dictionary. Yes, I totally can. What about, what would be a slightly higher level thing to say here? Maybe const graph equals, so keep track of adjacency in a dictionary. And graph or list, call it graph. I'm not sure how to, like that. I just kind of have to concretely say that I'm calling it graph. I don't know. Can't think of a reasoned motivation for calling it graph. But this is good enough. This is pretty high level. Specifying exactly what to call it seems kind of a little too concrete. If there's a better higher level reason for using the word graph or some other word, let me know. Graph equals an empty dictionary. Okay, cool. So now I've done this and the for loop, and the only thing left is return graph. That is a description of what to do. And so I'll see if I can return graph. Yep, I can recreate that. What would be a higher level? The graph is complete now, so it's the return value. Yeah, I feel like this is a pretty good programming construct right here. There isn't really a better way of saying this. Or maybe this is not very easy to represent in English is a better way of saying that. This is an idea that really doesn't come up in everyday English very often. Anyway, let's try running the test again. Cool, it worked. Actually, if somebody knows in Emacs how you would, like, instead of me having to do this over and over again every time I hit save, it'd be cool if I could have, like, a little icon down here that's red or green based on whether this passes or fails. I'm sure something like that exists, and if it doesn't, it could exist. That would be rad. It probably would not be too much to code up a solution to that. So now that I've done all of that, I've worked towards higher level. Now I'm going to try to, I'm not quite here yet. I'm going to redo the entire thing without any code from start to finish, but with comments. Oop. So this is a little bit harder of a test. Okay. Keep track of adjacency list, call it graph in a dictionary. Const graph equals an empty dictionary. For every node a, b in the list of edges, for const a, b in, no, of edges, then I'm going to, if there are no neighbors for a yet, so if not a in graph, maybe neighbors would be a better word for this. I think actually, yeah, neighbors would be a better word for this. I'll make that change after I get to the point where I can test whether it works. So first I'll get back to the code that worked before, then I'll try making the change, try these changes. We will call graph neighbors, rename graph to neighbors, and then what was the other one? Oh yeah, save a set of neighbors instead of a list. I think that's good. I'll get back to those later. To do. Cool. So I'm in the middle of doing this. So if there are no neighbors left for A, if there are no neighbors for A yet, node A has no neighbors to start with. So graph, yeah, I think calling it neighbors is really going to make this code a lot clearer. Graph is an empty list, and then if there are no neighbors for B yet, so if not B in graph, then graph of B is equal to an empty list. Copy that there, and whoop, that goes there. Okay. Then in the graph at computed node A, put node B on the list of neighbors. Okay, so graph at A dot push B, and then we're gonna do the same thing for the other way around. Graph B dot push A. Okay, so that's that, and then finally return graph. Alrighty, so now I'm gonna go back to the shell and rerun, and it still works. Cool. And I actually do have some things to try out here. Unfortunately, I don't have a test for build graph. I have a test for something that relies on build graph. So if I make these changes, they change what build graph returns, and it should be possible to work with that as well, but the other code needs to change to handle the different here. Instead of using a list, using a set, that part, the outside code, the code that calls this function, would need to know that possibly. I guess I'll go look at the other code and find out. But this one I should be able to do. So here, instead of graph, I'll call it neighbors. And then now I think the code reads a little better. So the neighbors of A is just an empty list. And here the neighbors of B is just an empty list. And then onto the neighbors of A, we will put B. And onto the neighbors of B, we'll put A. And then we return the neighbors. Yeah, that all seems good. But just to be sure that that didn't mess anything up, I'll go back here. Cool. That still runs, and it works well. Let's go look at build graph and how it's used. So here, graph is used. It returns graph. And then how is graph used? That's it. Okay, so it's only used right here. And then so graph, we pull out neighbors, and then const neighbor of neighbors. And okay, so let's see, how is neighbors used? That's it. Okay, so that's the only place. So that's the return value as far as changing the list to a set. This is the last place it will cause us any or make any changes. And we have of here. I don't know. Can you use of on a set? If so, then I actually don't need to make any changes. So let's go back to build graph. And here I'll do new set. And same thing here, new set. And then here we need to do add. And then let's see if that causes issues with this. It does not. Wow. Did I save? Yes, I did. Okay, that's cool. So yeah, so I feel like I actually am able to make changes, and that's great. So I'll just mark that as done. I am able to make changes to the way that this code works, and I understand the impact that that will have on other code, and that's why I do this recoding thing, is being more confident that I can do that. So I go make changes more quickly, and I know what changes to make. So now I'm going to try deleting everything and seeing if I can go do the whole thing from scratch. So first I'm going to go rerun this. It doesn't work. And then I'll go back to the description. So I should be able to rewrite the whole thing without comments. And I actually did this step already. So like that's pretty cool. All right, let me go back here. Nope. Here? Yes. Okay, cool. So I know that I'm going to want a bunch of neighbors. Const neighbors is equal to... Can neighbors be a set? A set of pairs? That's basically a dictionary. That's what an object is. Okay, so const neighbors. If, or no, let's see, for every A and B of neighbors, no, not neighbors, edges. So I'm going to go through the list of edges. My original problem is to take input that looks like this, so a list of lists, a list of pairs, and then turn that into a list of pairs again, but this time the key of the pair is what node, and the value of the pair is a list or collection of all the neighbors. Whereas here, it's not really key value pairs, it's pairs of things that are neighbors to each other. So like bidirectional, two directional, goes both directions, goes both ways. All right, so A and B, if the A is not in the set of neighbors already. So if this is the first time we're seeing neighbor A, then we want to say neighbors at A is going to be a new set. And then we'll do the same thing if not B in neighbors. So if this is the first time we're seeing B, actually, I don't think I said that before. I think my comment was different. So if this is the first time we're seeing A, that's what this if statement means. If A is not already one of the neighbors that we know about. This is a pretty high level and even another way of looking at why do this particular step. So that's the sort of thing that I really like about recoding. Oh my gosh, I can't type. Equals new set. Okay. And then we want to say neighbors at A dot add B, and same thing in the other direction, B A, and then return neighbors. Okay, let's see if that works. It does. First try, 0 deaths. I wonder how long this is.